We're going to talk about uncertainty Averse pushing with model predictive pattern trigger control. I'm from Birmingham, and one of the first authors as well is probably watching here is Michael, and I'm going to be presenting to you what we did. I think the intuition behind what we are trying to do is, for example, when we have this example of the drunken spider, you have, let's imagine you were a spider and you just came out of the local pub and you're really drunk, completely pissed, and you want to go back home. But we know that the shortest path to your house is basically to cross the bridge, but because you're so drunk and you are a spider, you hate water, you don't want to go to cross the bridge and risk falling into the lake. So in this case, when you have these disturbances, noise, or different sources of uncertainty, the optimal path of this spider is not actually the deterministic path that you'd have in the absence of noise or in the absence of uncertainty. A similar thing that we envision is when you're trying to learn a model of how an object behaves when you're pushing it. So in the initial locations of the object are in green, and the locations of the object after you apply a random push are depicted in red. But suppose that you didn't collect data in certain regions of the state space, so you have a gap in your data set. You didn't collect data there for multiple reasons. Maybe there are obstacles, or maybe this area was not kinematically feasible for pushing. Simply, you don't know what's happening there. You could have a uniform table with the same friction coefficient, but maybe in that area, actually, you could have sandpaper with completely different physical properties. And you don't want to push it. And we also show some results that we had in our robotic platform, which is a Baxter. So the main components of our approach is a forward model that we learn from experience, letting the robot push around an object. And then we connect this learned forward model with a path integral controller. So we've been playing around with different types of forward models. I'm going to describe to you in more details the first one, that's the one that we've been using, but we also did experiments with Gaussian processes, which are also able to predict uncertainty, incorporate uncertainty in their predictions. And we also tested with deterministic physics simulator. We use, as a forward model, an ensemble of mixture density networks. A mixture density network is basically a special type of neural network that outputs the parameters of a mixture. In this case, it's a Gaussian mixture model. So our mixture density network is basically outputting the parameters of a Gaussian mixture model. And we combine multiple of those MDN in an ensemble, so that at the end we have what we call a EMDN, an ensemble of MDNs. And it's able to predict what's the next state of the object when you have given the current state of the object and some given push that you can need to apply. So that's what we call a forward model. But the interesting thing is that if you train this forward model accordingly, then some people in DeepMind have shown that you can basically estimate the predictive uncertainty, which is the variance of our model, and also we can estimate the mean prediction of our model. So you can have something that behaves more or less like a Gaussian process, but it's not exactly a Gaussian process. The way we train this model is that we collect a data set via self-supervision, so we let the robot play around with the box. It restarts the box as it's doing now, and then it starts poking the object around, applying random pushes and observing what's the next state of the object. So in this way, we collect a data set of pushes that we can then train our model. So just to validate that our model is able to actually behave akin as if it was a Gaussian process, let's say, an approximation to a Gaussian process, we can, for example, lesion the data set that we collect, so that we have gaps in our data set. And we can see that our model is able to capture the output high predictive uncertainty depicted in green, the heat map below, in the regions that we don't have data, and low predictive uncertainty in the regions that we did have data. Then we define the controller using this type of forward model. The controller we can define in the context of the stochastic optimal control by defining first the cost function, which has two components, the running cost and the final cost. The running cost basically is an integration of the step costs, and these step costs And the final cost is just a penalty on how distance I am from the goal configuration that I want to achieve. So the step cost contains now uncertainty penalty, which allows us to dodge the regions of high predictive uncertainty. And we can do that using path integrals because our cost function doesn't need to be differentiable if we're using path integrals to solve the optimal control problem in this case. And also we have the desired state penalty as usual, and if you wish, you can also have the command penalty. So the problem here is that the sequence of optimal controls that we're trying to find is the sequence that minimizes the expectation of all possible trajectories that you could possibly have in your probability distribution of possible trajectories. It works more or less like this in practice. So you start with a given initial sequence of control commands, then you sample a variation of this sequence of control commands, which is basically a disturbance that can come from a Gaussian distribution, for example. You disturb your initial set of control commands with this variation, and then you forward simulate that using your forward model. So when you forward simulate, you're basically generating a trajectory. And this trajectory, as we've seen, is a sequence of states, actions, and because our model has predictive uncertainty, also the predictive uncertainty at that particular location in the state space. So we can repeat that many times, so we collect many trajectories, we sample them, so it's a Monte Carlo sampling strategy. You can see that some of these trajectories are good, some of these trajectories are bad. Some of these control disturbances that we generated, some of them, they minimize the cost function, some of them, they go in the wrong direction. So you can define a weight, like a softmax, that will tell us, okay, what is the best disturbance in terms of proportionally to all the other disturbances that we have. And this is basically the softmax that we can use as a weight. And then if we average those control command updates, calculating the weighted expectation, we have an approximation of the gradient that we want, the direction that we want to update our control commands so that we're going to minimize our cost function that we define. And then we do that iteratively over time, and then we execute the first action, and we carry on again, executing pushes like that. So the results we have by defining a controller like that, you can achieve in simulation, for example, uncertainty averse behavior. So that in this case, for example, you see a point mass box being pushed and avoiding the regions of high predictive uncertainty on the right, but without the penalty to the uncertainty, it tends to follow a straight line, ignoring the region of high predictive uncertainty. So you can have a trade-off between going to the goal as straight as possible or dodging the regions of high predictive uncertainty. This is sometimes hard to tune. So one alternative is to optimize a trajectory using a similar update as I described before, a path integral update, but now we are optimizing a full trajectory, and that is going to dodge the region of high predictive uncertainty, but then after optimizing this trajectory, you can simply follow it. Final results, we have deployed this type of controller on a real robotic platform using different types of forward models. The first on the top is a Gaussian process. In the middle, you have our EMTN model. And on the bottom, we are using a deterministic physics simulation to predict the next box location. And you can see in our experiments, this is just a single trial that I'm showing to you. But in our experiments, we found that the learned models, they tended to reach the goal with less pushes than the physics simulator. So as a conclusion, we integrated learned forward models that are able to estimate the predictive uncertainty of the predictions. We combine these learned forward models with model predictive path integral control. We are able to penalize uncertainty. We are able to pre-compute trajectories that minimize uncertainty along the state action space. And then this is a step towards what we think as robust pushing. And as future work, we've been going in the direction of extending pushes to low arm pushing, and also taking into account impedance in the future. Thank you.